For my project, I chose question number 1. In the problem, there is a 4-kilometer block on a track with negligible friction except for this 0.25 meters right here, which is rougher than the rest. The block starts against a 8,000 Newton meter spring, and it initially is compressed 6 centimeters. And when released, the block moves all the way up the track and then falls back down. And then the second time the spring compresses only 5 centimeters. So what we need to find out is the coefficient of friction for the rough part up here. So what we know is that energy is conserved unless there is any work. So the total initial energy of the block when it's here should equal the final energy of the block after it goes all the way up and all the way back down, unless there's any work. And in this case, we know that there's work because there's less energy after it goes up and down once because there is less spring compressed. So we know that this friction area here does work because there's a force of friction, and work equals force times distance. So if there's a force, there's work done on the block. So first I calculated the initial energy, which is all potential spring energy, by using the equation 1/2 k delta x squared. And we know that K of the spring is 8,000, and the spring is compressed 6 centimeters, so that's 14.4 joules. And then I calculated the energy after the block moves up and down once and is compressed 5 centimeters. So I used the same equation and found that that was 10 joules. So we know that 4.4 joules were lost. So then using our work equation, we set work equal to 4.4 joules. And we know the distance is equal to 0.25 meters because that's how long the rough area is. And so then we need to find the force. So we know that the static friction force equals the normal force times the coefficient, which is what we're trying to find. So to find the normal force, I drew a force diagram of the track moving along, or the block moving along the track. And as you can see, I didn't put all the forces maybe, but these are the y component forces, and the force of gravity downwards has to equal the normal force upwards since the block has no movement up and down. So the force of gravity is equal to mg, so we know that the normal force must also equal mg so that the net force here will be 0. So I said the net force equal to mg, and the mass of the block is 4, and the gravity is 9.8. So that equals 39.2 newtons. So then, if you plug that back into the force, the normal force is 39.2 newtons. And then, this is what we're trying to find. So then if you plug that back into the work equation, the distance is 0.25. And then that part. And then you're setting that equal to 4.4. And when you plug that into a calculator, you find that mu is equal to 0.224, approximately. And that's the first part. Next, what we're trying to do is just describe the motion of the block from when it's initially released from the spring until it finally stops. So we know that the initial energy of the block is 14.4 joules, and then after it goes up and down once, it has 10 joules of energy. So if we start with 14.4 and subtract 4.4, after one time it has 10 left, after 2 times it has 5.6, and after 3 times it has 1.2 joules left. So the block goes up and down 3 times and then has 1.2 joules left. Now what we want to find is that when it has 1.2 joules left, how far is the spring going to compress when the block comes back and hits it? So you use the energy formula for potential spring, 1/2 k delta x squared. And you set it equal to 1.2 because that's how much energy it will have. And we know that K is 8,000, and we're trying to find delta X. So when you plug that into the calculator, you get that delta x is 1.73 centimeters. Finally, we have to find what happens after the spring is compressed 1.73 centimeters and block bounces back. Since there's no friction anywhere here, it will retain the 1.2 joules of energy until it starts going through this rough section here. So what we're trying to find out is how far into the rough section the block will travel before it comes to a stop. So we're trying to find how much of this will do 1.2 joules of work on the block. So I use the work equation. Work equals force times distance, and you set equal to 1.2. So we remember from before that the force is friction, and it's equal to the normal force, which was 39.2, times the coefficient of friction that we found before, which was 0.224. And that force is equal to 8.78 newtons. So when you plug that back into the work equation, 8.78 times distance, and you set it equal to 1.2, you find that the distance is equal to 0.137 meters, or 13.7 centimeters. So from when the block starts, it goes up the ramp and down the ramp 3 times, and then is compressed 1.73 centimeters after the 3 times, and then bounces back and goes into the rough section 13.7 centimeters. And then it stops, comes to a rest. And that's the entire motion.